Hi, my name is Drew Koh, and I work in the timber unit with the Central Valley Regional Water Quality Control Board. Today I'm here to give a talk on the hydrologic impacts of rural roads, and I'm also going to be talking about some water quality issues as well. So just a brief overview of the presentation. First thing that we're going to talk about is how hydrologic processes are affected by rural roads. We're also going to be talking about how runoff pathways are also affected. Then we're going to transition into a talk on the water quality impacts of rural roads with a special emphasis on erosional impacts from roads. And then we're going to take what we learned from the first two parts of the talk, and we're going to talk about ways to mitigate those hydrogeomorphic impacts from roads. So before we get into hydrologic impacts, I think it's important to know some of the basic concepts in forest hydrology. There are four basic types of runoff processes on a forest hill slope. The first one would be Horton overland flow, and that's the easiest way to think about that is when the rainfall intensity exceeds the infiltration capacity of the soil. So if it's raining harder than your soil can infiltrate, you start getting overland flow. The second type of runoff process is groundwater. That's basically everything under the water table, and it's saturated all year round. And the third type is subsurface storm flow, which is also referred to as transient groundwater. Basically, as the water table fluctuates, some of that area is called the beta zone. That area is prone to kind of lateral storm flow during rainfall events. And then the fourth type is saturation overland flow, and that happens when the water table, the elevation of the water table actually exceeds the elevation of the soil surface, and you basically have water popping up onto the soil. So again, Horton overland flow is when the infiltration rate exceeds the rainfall rate, and it's very common in dry and subhumid climates, areas that have thin vegetation such as desert ecosystems. And it's also quite common when there's extensive soil disturbance, for example, soil compaction. The one thing you should know about Horton overland flow is that it's not very common in undisturbed forested areas. So if you start seeing a Horton overland flow in a forested area, you probably have disturbance. Subsurface storm flow, that's a little acronym there, SSF. That typically occurs on steep hill slopes where you have permeable soils overlying relatively impermeable bedrock or regolith. And it's the most common runoff process where you have a humid climate with lots and lots of vegetation. Forested areas in California, that would be your dominant runoff process. So the one thing about road surfaces is that they are highly compacted, they have high bulk densities, and they have little or no pore space below the running surface. And as you can see here, I have a table of published values of saturated hydraulic conductivity. Think of that as sort of an infiltration rate at saturation. And as you can see here, the values vary by about 4 orders of magnitude, but they're very, very low. Most of those are under 1/5 of an inch per hour, so and well below that as well. So in many cases, the rainfall rates will exceed the infiltration capacity at saturation on these road surfaces. Here's a figure from a paper by Alan Ziegler. There on the y-axis, you have saturated hydraulic conductivity, and then you see those horizontal lines are representing sort of median or mean rates of saturated hydraulic conductivity for various land use features such as forested areas, agricultural areas. But I want to draw your attention to those horizontal lines representing roadside edges and road surfaces. As you can see, there are at least an order, if not 2 orders of magnitude below land use types such as forest and agriculture. And those little circles in there represent discrete rainfall events. And most of those rainfall events exceed the median value of the saturated hydraulic conductivity. And so what this tells us is that most rain events are producing Horton overland flow on road surfaces. The other thing that roads do is that when you cut transient groundwater perched. And when this happens, you start intercepting subsurface storm flow. And what researchers have found is that the interception of subsurface storm flow by cut slopes can be responsible for up to 95% of the total road runoff in humid forested areas. And so what this does is it takes very, very slow soil water and turns it into fast-running surface water. And by intercepting and kind of changing the process here, you can increase the velocity of the runoff by up to from 10 to 10,000 times greater than if it was actually running laterally in the soil profile. And what this really does is it increases the rising limit of the hydrograph. So where is the interception of subsurface storm flow common? It's common when your cut bank intercepts, or when the depth of your cut bank exceeds the depth of your soil. And so anytime you're exposing that soil interface, you're likely going to be intercepting subsurface storm flow. And as far as portions of the landscape that are susceptible to it, it typically occurs on areas with thinner soils, on the lower slopes, and also, or on higher slopes, because that exposes the, or that increases the height of your cut slope. And it also occurs typically on mid-slope to lower valley positions on the landscape. So roads do not only affect runoff processes on the hill slope, they're also capable of affecting runoff processes that occur in channels. An example of this is when you have stream diversion by a road. Many times, especially on legacy roads, you have instances where roads were built right across streams and the streams were never piped across the road. Or sometimes the pipes become blocked and the road actually intercepts or pirates the stream flow from the channel. And so really both these changes to hill slope runoff and potentially channelized runoff can really create some downstream impacts and downslope impacts in the form of initiating gullies and also initiating landslides. As a result, many of these roads can deliver this excess runoff to the channel, especially close to stream crossings. Now, when we refer to the linkage between roads and channels, we refer to it as connectivity or connectivity to surface water. And this happens usually very close to the road and stream interface at places like crossings. This is a schematic here showing areas where you do get that kind of linkage. You have connectivity at crossings, such as bridges, connectivity at fords. But you can also have connectivity when you're routing enough runoff across the hill slope that is able to make it all the way to the channel without infiltrating. And ideally, what you want to do is you want to take advantage of the infiltration capacity of the hill slope and drain it before to an area of high infiltration. And that prevents the runoff from eventually reaching the channel and thereby decreasing connectivity. Now, connectivity is largely a function of things like rainfall. Here's a schematic here showing the percent connectivity of a road network as a function of mean annual precipitation. Those solid dots represent roads that have engineered drainage structures in place, and then the open circles represent road networks that have basically no drainage in that also stream density is also because that controls the number of stream crossings, and stream crossings are where you typically get the highest degree of connectivity. So we kind of know what roads do on the hill slope at the local scale. So do these impacts end up translating down downstream at the larger watershed scale? To really answer this question, we have to look at the published literature, studies done in the paired watersheds in the Pacific Northwest, and also it's helpful to look at modeling studies because sometimes the paired watershed studies are limited in the range of treatments. So for this, we were looking at studies that represent watershed areas ranging from 61 to 759 acres, and the data is from both the H.J. Andrews and Casper Creek watersheds. That H.J. Andrews is in the Oregon Cascades, and Casper Creek is in the Coast Range of California. Both of their watersheds, paired watershed studies showed no increases in mean annual peak flow due to roads. The only paired watershed study that did show effects due to roads was in the Oregon Coast Range, where they found that there was detectable effects on peak flows when roads occupied more than 12% of the watershed area. Now that was a very, very small watershed that they ran the study on, and of course, as you shrink a watershed down, road area can make up a larger percentage of the total watershed area. And just to put that in perspective, typically, once you're talking at larger scales, industrial forest lands only have about 2 to 4% of the watershed area occupied by roads. So it's very hard to achieve that 12% threshold that was demonstrated in the Oregon Coast Range. So again, paired watershed studies can be rather limiting at times. It's hard to separate out the effects of roads versus harvest. So to do this, lots of people have turned to modeling, and one particular model that's been used in forest settings is DHVSM. That stands for Distributed Hydrologic Vegetation Simulation Model. It's a distributed, physically based numerical model that simulates all the relevant, basically runs water budget and energy budget for every single grid scale or grid cell in the model. And what they found was that the effects of forest roads were largely equivalent to harvest. And that's pretty interesting because if you think about 2 to 4% of the watershed area being occupied by roads and anywhere from 20, 30, 40% by harvest, it shows sort of the large effect that roads have on a per unit area relative to harvest. What they also found was that there was an 11 to 12% increase in the mean annual flood per 2% of area disturbed by roads. So again, if you have 2 to 4% typical in a industrial forest land, then you're generally going to have between a 10 to 20% increase in the mean annual flood, potentially. And then they also wanted to look at whether the effects between roads and harvest were additive or synergistic. Synergistic being, or referring to it being greater than the sum of its parts. And what they found was that they are essentially additive. There is not this kind of snowballing effect when you add roads onto harvest. The one limitation with using these models is that they're not really, they don't end up really accurately representing the true processes on the hill slope because during the model validation or calibration and procedure, there's a lot of knob tuning that goes on. And by the end of it, the processes that you're representing in the model are kind of skewed in order to match the watershed outputs in the model itself. So There's, you know, models have their benefits, but once you start getting away from representing true processes, they start becoming problematic. So now that we know about runoff impacts, I want to talk a little bit about water quality impacts. That's what we're all here to listen to in these talks. The first concept is that to have water quality impacts, you have to have erosion plus delivery to a water body. So you have to be eroding material, and you also have to have connectivity to the channel network. So erosion is basically a function of the amount of energy applied to the road prism, and also a function of the erodibility of the road prism. Erosive power is largely a function of the runoff depth and the slope of the flow path. And this concept of depth times slope as a predictor of erosive power, it's a pretty important concept to keep in your mind. So when you're looking at mitigating, you're always looking to decrease the amount of runoff and really that depth times slope term. Runoff depth is controlled by a variety of factors, but some of the biggest ones that you should be aware of is that one of those is distance between water breaks, or the length between drainage structures. And it also is affected by the degree of runoff concentration, and different engineered segments will have different degrees of runoff concentration. A ditched road segment will have a tendency to concentrate runoff, whereas an outslope road segment will have a tendency to disperse it. Here's another schematic kind of showing this concept. You see down there on the x-axis, it says distance from ridgetop or water break. Really, that distance kind of dictates the dominant erosion process that's happening on your road segment. If you have a very, very small distance, all your road segment's going to be subjected to is rain splash erosion. That's going to be a lower magnitude of erosion that comes off of rain splash. As you start increasing that distance between water breaks, you start transitioning into sheet erosion. And once you start getting into rill and gully erosion, the magnitude of erosion goes up considerably. Rilling and gully erosion. So the degree of concentration is also important, as I suggested. And one of the things that can really concentrate runoff is wheel rutting. And this is a schematic, a figure showing sediment concentration on wheel ruts versus just sort of a planar surface, a planar plot on the road surface. And as you can see here, there's about an order of magnitude difference in the peaks between just kind of sheet wash on the road versus the erosion that's coming off on a wheel rut. So we also want to reduce rutting on our road surfaces. Erodibility is the other property that really kind of dictates the degree of water quality impacts. And erodibility is largely a function of the geology, in particular, and geology is a big determinant of your soil properties, things like size fraction and cohesion. And some other anthropogenic factors that can influence erodibility are things like traffic, road maintenance, and also the age of a road. Here's a native road segment in the Butte Creek watershed. That's in the northern Sierras. And this soil is derived from lithified volcanic mud flows. It's actually there's a very high rock fragment content in this soil, and it naturally armors itself against erosion because runoff has a hard time moving these larger size fractions of rock. So those rocks really provide a resistance against the erosion of the underlying material. And so this is a relatively, this particular soil has low relative erodibility. This is a road segment in decomposed granitics, and this is quite different. It has no large rock fragments in it. The soil is fine sand and silt that's very erodible size class material. And there's very little cohesion, and so you essentially have rilling that develops within 10 to 20 feet of slope distance. So these are sort of end members in terms of erodibility. Traffic is a very important determinant erosion rates because it increases the erodibility of the running surface. It increases the amount of fine material that's easily transportable by runoff. And this is a figure showing sediment production as a function of axles per day or number of trucks per day. And that's quite a large scatter, but there is a positive trend. And the literature is full of examples of the effect of traffic on sediment production rates. In particular, Reed and Dunn's work from 1984 showing orders of magnitude increases with varying degrees of traffic. Maintenance is another important factor controlling the erodibility of the road. As you see here in this picture, here's a tractor grading a road, and what it does is it really creates a lot of fine-grained material that is very easily transported by runoff. This can happen on the road surface itself or in the ditch. There's plenty of examples of the high sediment production rates following the pulling of ditches. And so we should be wary about where we're grading our roads. And as we know, also, erodibility is going to be a function of the age of the road or time since the last maintenance or time since traffic. Here's a schematic here showing grading. After they graded in 1996, they show erosion rates for the following 2 years following grading. And what you see here is a negative exponential decline in sediment production as that fine material your supply of fine material has been diminished to the point to where your erosion rates are essentially back down to a background level. Again, these impacts are highly dependent on the degree of linkage. It's hard to get too excited about the degree of erosion when it's up on a ridgetop and it will never reach a stream. But we need to really factor or really emphasize our mitigation measures on the places that are directly linked to the channel network. Again, this is an important point to reiterate. Linkage is most common at road and stream crossings. This is where we should place most of our focus. And the water quality impacts at these particular points are typically chronic in nature. And generally, the sediment is fine-grained. Now, sediment can be delivered away from road and stream crossings, but they generally happen when roads are close to streams, roads within riparian zones, roads directly above stream crossings. And you can have even mid-slope roads that deliver sediment if they are discharging large enough amounts of runoff or sediment onto the hill slope. And of course, if you're starting to initiate gullies or landslides, you can deliver from much further away from the channel, and so we really want to avoid initiating both gullies or landslides. Here's an example of a gully that's initiated by road runoff. This is taken about 150 feet above the stream, but that gully continues all the way down into, and that's Butte Creek actually below. It's a salmon-bearing stream. showing the travel distance of sediment below drainage outlets as a function of hill slope gradient. And as you can see here, most of the studies show that sediment, if you're further than about 150 feet away, the sediment is usually dissipated onto the forest floor, but there are some instances where you need at least 200 or 300 feet of slope distance before the sediment and runoff are dispersed onto the hill slope. Another place where you have water quality impacts is when you have the pirated stream crossings. And since you're basically taking the runoff from a stream channel and dumping it onto an unchanneled hill slope, as you can imagine, you can get quite a bit of erosion. Here's a picture of a gully that was initiated by a diverted stream crossing in the Sierras. And one of the worst case scenarios is when you start to initiate mass wasting on the hill slope. That's when you start getting into very, very high magnitudes of erosion and hence greater water quality impacts. This is a picture that was taken up in the Northwest Cascades in Washington. This was an old legacy road that had some undersized crossings over intergorge landforms and bedrock hollows, and when those pipes become plugged or when the drainage breaks down, you start putting water onto unstable hill slopes and you start generating landslides, and these landslides run all the way down to the channel. So the sediment that we deliver to the channel, it's generally going to be fine sediment, and what this does is it increases suspended sediment concentrations and turbidity. These have impacts on things like macroinvertebrates and fish. So things like site feeding are strongly affected by turbidity in the stream. Here's a picture showing what increased settleable materials will do. This is generally going to be the sand-sized material and larger, and what it can do is it can fill in pools and fill in gravels. And when you start initiating landslides from roads, it can deposit a tremendous amount of material in the channel. And this is a picture showing a large landslide deposit, and the channel is basically incising through that deposit. And that can be a source of fine-grained material for decades. So knowing what we know about the hydrologic impacts and the hydrogeomorphic impacts of roads, how do we mitigate the water quality impacts from rural roads? Well, if you remember, we want to drain roads frequently. We want to decrease that slope length between water breaks. So if we drain roads frequently, we're not going to have as much water dumping over the sides, able to connect to channels. And we also want to disperse rather than concentrate runoff, because if you remember, dispersing results in lower erosive power than the concentration of runoff. And we also want to avoid excess stream crossings, because near the streams. That's our area where we have where linkage is most likely. So if we focus special attention on those areas, we can decrease some of those water quality impacts. And then we also want to minimize cut slope flow path interaction. So we want to try to avoid putting roads on really steep slopes, thin soils, areas where we can intercept a lot of runoff and create downslope or downstream impacts. We also want to decrease the erodibility of our road prisms by hardening running surface, particularly those that are connected to channels near stream crossings. And we also want to preferentially armor or harden these surfaces on roads that get a lot of traffic and on new road construction, because those are the ones that have the highest initial rates of erosion. We also want to avoid unnecessarily grading hydrologically connected road segments, because that again can also spike erosion rates, and those always get delivered to the channel network. And then we also want to manage the use of our roads during the wet season, because once you start getting rutting on the road surface, it can start breaching your drainage structures, and it just increases the erosive power of runoff. We want to decrease the likelihood of stream crossing diversion by oversizing culverts to pass flow, sediment, and debris. And we also want to construct things like critical dips or diversion potential dips. These are structures that keep the channel in the channel rather than diverting them onto the road. We also want to anticipate crossing failure. So we want to harden our fills and basically manage for when that big storm comes along. We also want to prevent gulling and the mass wasting below roads by decreasing runoff at discharge points, trying to drain to planar